Before I start to describe how the forces of nature arise, I need to cover something called Noether's theorem. If you've never heard of Noether, then it really is worth looking her up. Her work is absolutely central to everything that I'm going to describe, and she really deserves to be far better known. If you look up Noether's theorem, then you'll either get a page full of maths, or you'll get a simple statement along the lines of, for every symmetry, there is a conserved quantity. Now, without a bit more explanation, that might not be very helpful, and you'd essentially be asked to just take the statement on trust. I want to chart a middle course by giving you a concrete example of Noether's theorem that I hope will convey the essence of it without going too deeply into the maths. And since we're about to discuss where gravity comes from, what better example to choose than gravity itself? So for our example, we're going to give some unfortunate student a cannonball and tell them to carry it up a high hill until they get to the cliff edge at the top. We're using a dense cannonball because we want to ignore air resistance and terminal velocities and all that sort of thing. So once at the top of the cliff, the student is told to release the cannonball, which starts to fall straight down. It falls slowly at first, but gradually starts to pick up speed. This is our first observation. The cannonball's speed increases over time. Now, the cannonball's speed increase is a reflection of the fact that its energy of movement, its kinetic energy, is increasing. But we all know that energy cannot be created or destroyed. If its kinetic energy, its energy due to its motion, is increasing, then it must be getting that energy from somewhere. When the ball was carried up the hill, it was given gravitational potential energy. This is energy that it has due to its position in the gravitational field. That didn't come from nowhere either. The student had to do work, probably rather a lot of work, to carry it up the hill. This is our second observation. The potential energy is position dependent. There's more potential energy at the top of the hill than there is at the bottom. So as the cannonball falls, it is converting potential energy, which is position dependent, into energy of motion, which is time dependent. In the language of physics, or the physics that we're going to use, the potential energy is not a symmetry of position. If you change the position, the potential energy changes. Things are different up there from down here. Now, some Olympian god gets fed up with planet Earth and declares it to no longer exist. Suddenly, there is no gravitational potential energy. This situation is symmetric with respect to changes in position. If you change position, then the potential energy remains exactly the same. With no change in potential energy, as the cannonball changes position, there is nothing to give it any more energy of motion. So it stops accelerating and continues to move at whatever speed it was moving when the Earth disappeared. This is the essence of Noether's theorem. You have something that changes over time because of some asymmetry in the situation. Conversely, when you see that the situation is symmetric, as it is now, the time-varying quantity, the speed of the cannonball, stops varying. In other words, it is conserved. This is Noether's theorem. For every symmetry, there is a conserved quantity. If you know a bit of physics, you probably think, well, there's nothing really interesting happening here. This is just a restatement of Newton's second law, force equals mass times acceleration. When there was a force, a gravitational force, the cannonball accelerated. When we took the force away, we took away the Earth and its gravitational field, then the acceleration, the force, became zero. and so the speed remained constant. All we've really done is rephrase Newton's second law in this language of symmetry and conserved quantities, which is the same language that is used in Noether's theorem. Noether's theorem just happens to be much more general than this, and we will use that generality when we examine how the forces of nature arise.